This section's on 4.3 quadratic functions and their properties. The objectives are graph a quadratic function using transformation, identify the vertex and axis of symmetry of a parabola, graph a quadratic function using its vertex, axis, and intercepts, find a quadratic function given its vertex and one other point, and find the maximum or minimum value of a quadratic function. So a quadratic function is a function of the form f of x is equal to ax squared plus bx plus c. Some things you should know about this is the plus c part. This is going to end up representing basically the y-coordinate of your y-intercept. So our y-intercept here is always going to end up being 0, c. And the a in front of the x squared part, that value, if it's greater than 0, that means it's going to be a positive value. And that will tell us whether the parabola is going to open up. So I'll just draw a little parabola here opening up. And if that a value right there happens to be negative, that means a is less than 0, then that means the parabola is going to be opening down. All right. So here in this form, a, b, and c are all real numbers with a not equal to 0. And the domain of a quadratic function is going to always consist of all real numbers. So that's always going to be true for any quadratic function we're working with. Quadratic function, right? So it's got to be a quadratic function. And if we are able to complete the square, the quadratic function can be expressed in the form that we call vertex form. F of x is equal to a times the quantity x minus h, quantity squared plus k. And this is vertex form. The a is still going to represent that same a from the first form. If it's positive, it's going to open up. If it's negative, it's going to open downward. And you can also find the vertex immediately by looking at an equation in this form. That's why it's called vertex form. H comma k is going to represent our vertex. If you have a hard time figuring out what h is, one way you could do it is you could set that x minus h part equal to 0 and solve for x. And that will be a quick way of making sure you know how to find that x coordinate of the vertex. So yeah, those are two major forms here that we use to write our quadratic functions. Let's go ahead and do number 1 here. Use transformations to graph the following function. F of x is equal to x squared plus 3. So if we're going to use transformations to graph this, our original function or our basic function, or remember I used to call it our parent function, in this case would be y equal to x, I don't mean cubed, I meant x squared. And since we're adding 3 to this, we're basically what it's doing, it's going to be shifted up 3 units. Our parent function will be shifted up 3 units. So I'm going to go ahead and plot the vertex of our parent function up 3 units, which will land us right at 0, 3. And then over 1, up 1 to each side, over 2, up 4 to each side, to the left and to the right. And that's the pattern I told you guys to memorize for that basic function. And then we can connect our points, and there is our graph. Okay. That looks good. So let's go ahead and label the ordered pairs. That's going to be 0, 3 for the vertex, 1, 4, and then the opposite side, negative 1, 4, and then we've got 2, 7, and negative 2, 7. And we call this graph, the graph of this function, a parabola. And notice that it is symmetrical on both sides of the y-axis. It's got an axis of symmetry that actually goes down the y-axis. The equation of that axis of symmetry is x equal to 0. And we call that the axis of symmetry. That means the graph is symmetrical on both sides of that line. So that's the way let me go ahead and label the equation of this function here. F of x is equal to x squared plus 3. Yeah, let's go ahead and also write down the domain and range. I know it didn't ask for that, but we should know how to find the domain and range of any one of these functions that we're working with here. The domain is all real numbers, so there's a couple of ways we could write that. We could write that as the open interval from negative infinity to infinity, or the set of all x such that x is an element of the set of real numbers. The range is going to be the half-closed interval from 3 to infinity, or the set of all y such that y is greater than or equal to 3. All right, so I think that pretty much covers everything for that first problem. Let's go to the next problem. Number 2, use transformations to graph the following function. F of x is equal to negative 2x squared plus 6x plus 2. In order to use transformations to graph this, we're going to have to complete the square. Yay! Everybody loves to complete the square, so this will be lots of fun. Okay, let's go ahead and see what we need to do here. I've got f of x is equal to negative 2x squared plus 6x plus 2. And you see this negative 2 for our a? What we're going to do with that negative 2 is we're going to factor out a negative 2 just from the first two terms that we have here, okay? So I'm not going to factor it out from the 2 at the end, just from the first two terms. So let's factor out a negative 2. That's going to leave me with x squared minus 3x. And then I'm going to push that plus 2 out here outside the parentheses. Now, in order to complete the square, I need to add something inside the parentheses and something outside that's going to balance out and make sure it maintains my function or my equation, you know, in equivalent form. We're going to take this, well, first let's review what's the formula we use for completing the square. We use b divided by 2 squared. So I'm going to take the negative 3 divided by 2 and then square it. That'll give me 9/4. 9/4 is basically what we're going to add inside the parentheses. Now I know it looks like we're just adding a 9/4, but we're not really adding a 9/4. We're actually adding something else. You see that negative 2 in front of the parentheses? Let's just pretend I said, oh, I want to distribute it to simplify this. We don't really actually ever distribute this when we do this process, but I'm trying to show you what we're really adding. If we were to distribute the negative 2 to the 9/4 that's inside, you got to ask yourself, what would you end up with? And that's what you're really adding. So let's go ahead and multiply. Negative 2 times 9/4 is going to give me negative 18/4. And if I reduce that, divide by 2 to the numerator and denominator, I get negative 9/2. So this number is what I'm actually adding. So you are actually adding this, a negative 9/2. So in order to maintain balance or maintain this as an equivalent equation, we need to add the opposite of this value. The opposite of a negative 9/2 is a positive 9/2. See, now this will make sure it looks like I'm adding a 0, since these two things will cancel out with each other. Okay, now we can factor out that trinomial. If I factor it out, it's going to give me x minus 3/2 quantity squared, because we turned it into a perfect square trinomial. And then plus, I'm going to have to multiply by 2 to numerator and denominator to get a common denominator to add these numbers together at the end. So it'll be negative 2 times x minus 3/2 quantity squared plus 4/2 plus 9/2. 4/2 plus 9/2 is going to give me 13/2. And now we have accomplished it. We have written this in vertex form. They didn't ask us, oh yeah, they did say use transformation. So that's kind of like asking us to write this in vertex form, right? Because we need to know what transformations we need to use. So now that I have it written in vertex form, the first thing I would do is I would actually find the vertex, because the vertex is going to give us like a starting point. So let's write that down. Our vertex is going to be, it's going to be 3/2 comma 13 halves. Now remember, if you're having a hard time seeing how I got the 3 halves, then I would suggest you take what's inside the parentheses, set it equal to 0, and solve for x in order to understand why I'm using positive 3 halves. And that might help you remind you why it's got to be a positive 3 halves in here. Now, if that's kind of a hard, number to recognize, it's like, where am I supposed to plot this? You might want to rewrite this as mixed numbers. So this would be 1.5, comma 6.5. So that might be easier for you to plot that point because it might be easier to locate. So let's go ahead and go to 1.5 and then go up 6.5. And that's going to get us to our location of our ordered pair. And this parabola is opening downward. I would look at that -2, the a value, to see that it's opening downward because it's negative. And then because it's -2, I know it's going to get vertically stretched by a factor of 2. Let me go ahead and write this out. This parabola, if I were to compare it to the parent graph, is going to be vertically stretched by a factor of 2. And because it's negative, it's going to be reflected across the x-axis. Okay, so now we're ready to go ahead. And what I'm going to do here is I'm going to draw just a quick sketch of the parent graph, but I'm going to do the parent graph that opens downward. So this is like me graphing y equal to -x squared. So normally we go over 1, down 1, over 2, down 4. Because I'm going to have to vertically stretch this parabola by a factor of 2, I'm going to multiply all the y values by a 2. So normally we went over 1, down 1, but this time I'm going to go over 1, down 2. Over 1, down 2. Over 1, down 2. And I normally go over 2, down 4. But 4 times 2 is 8. So this time we're going to go over 2, down 8. And it looks like it didn't plot that last point there. I'm going to have to go back and fix that point and make sure it goes down 8. Let me make sure I count these and it's going down 8. And there should be one more, I think. And just once again, I'm just struggling with my tablet a little bit. There we go. There's our graph. Now let's go ahead and label these points so we know exactly where these points are at. Our vertex, we already said about what our vertex was. Our vertex is at 3 halves, comma 13 halves, or if you want to write it as a mixed number to help you, be more aware of where it's located, that's fine. This point right here, this is the y-intercept. This is at 0, 2, and it's reflected on the opposite side, right, of the axis of symmetry. So this point over here, if I were to go over the same number of units on the opposite side of the axis of symmetry, would land at 3, I believe it's at 3, comma 2. And these other points that I have right up here, let me go ahead and write this in right about here. This looks like it's going to be at 2.5, comma 4.5. And this other point that's on the opposite side, it's going to be at 1/2, comma 4.5. So there is our parabola, and I went ahead and drew the axis of symmetry and labeled it with x equal to 3 halves. Okay. Okay, let's go ahead and write down the properties of quadratic functions here for the next problem. We're just going to go ahead and fill in this chart. Now, for some of these spots that I'm going to fill in, I'm going to try to erase that line that's in between, because there's no sense in writing two different formulas for finding the vertex when it doesn't matter whether a parabola opens up or down. You know, the vertex formula is the same. And the formula for finding the axis of symmetry is also going to be the same. And same thing with maximum and, well, no, the maximum minimum, concavity and maximum minimum, we're going to leave those lines there, but we're going to erase the one for the x-intercepts. And I think we can also erase the one for the y-intercept as well. And I think that's about it. All right, so I think we're ready to start filling this in now. Let's go back up to the vertex. In order to find the vertex, we're basically going to use this formula. It's going to be the ordered pair. I'm sorry, I apologize. It's just, this tablet sometimes wants to write nice and sometimes it doesn't. And right now it doesn't. So it's going to be the ordered pair negative b over 2a, and then that's going to be the x value, and the y is going to be f of negative b over 2a. The axis of symmetry is going to be x equal to negative b over 2a. Concavity, if it opens upward, we say that this is concave up. If it opens downward, we say this is concave down. If it opens upward, we're going to say it has a minimum value. And we also sometimes refer to this as a local minimum. And if it opens downward, then we say it has a maximum value, or we might refer to this also as a local maximum. The x-intercepts. The x-intercepts, we're going to basically just use the quadratic formula to write down the formula for these. So if you imagine you're setting the y equal to 0 and you're solving for quadratic equation, you would use like the quadratic formula. So the quadratic formula is going to give us the x-coordinate of our x-intercepts. And the way we know how many x-intercepts we have, we can always look at the discriminant. That's the part that's underneath the radical of the quadratic formula. So if your discriminant, which is the b squared minus the 4ac, if that's equal to 0, then that basically means you're just going to have one x-intercept. And that can only happen when your vertex lies on top of the x-axis. So this means you have one real x-intercept. Now let's say your discriminant is greater than 0, then that means you're going to have two real x-intercepts. It'll be two real values. They might be rational or they might be irrational values, depending on the number. If it's a perfect square inside there, they're rational. If it's not a perfect square, then they're irrational. And if your discriminant is less than 0, then there's going to be no x-intercepts. That means it's just not going to cross the x-axis. And that happens sometimes. So that happens when you have a negative value inside of your radical. The y-intercept. If you want to find the y-intercept, basically you just have to set your x equal to 0 and then just solve for y. So I'm going to put here, the y-intercept is basically going to be just 0, f of 0. And the domain and range, the domain doesn't matter whether it opens up or down, the domain is always going to be all the reals. So the open interval from negative infinity to infinity, or the set of all x such that x is an element of the set of real numbers. The range, that will change. So depending on whether it opens up or down, right, this is going to make a difference. If it opens upward, then the lowest value is going to be that minimum value. So we'll start off with that value. So it's going to be the half closed interval from, and you're basically going to use the y value of the vertex. So remember what we said the vertex is. In this case, the vertex is negative b over 2a, f of negative b over 2a. So that's the y value, that second coordinate. So that's basically going to be where our interval starts at, because that'll be the lowest value, and it's going up towards infinity. So we're going to write here the half closed interval from f of negative b over 2a, comma, infinity. Open on infinity, it's always open on infinity. And then here, if it opens downward, right, the vertex is still the same, negative b over 2a, comma, f of negative b over 2a. So f of negative b over 2a would be the largest value for y, and the smallest, well, we know negative infinity is not a real number, but we use it in interval notation. So it would start off here, open at negative infinity, and then up to f of negative b over 2a. I should have put closed on that negative b over 2a, so I made a mistake there. Make sure you put down that it's closed on that interval. That should be half closed. Open on the negative infinity, and then we would have been closed on that y value. Okay, number 3, use the properties of the quadratic functions to graph f of x is equal to 3x squared plus 3x minus 2. I can tell that it opens up, so it's going to be concave up. I can also tell that the y-intercept, or the y-coordinate of the y-intercept, is going to be at negative 2, so the y-intercept is 0, comma, negative 2. If I want to find values, the value of the axis of symmetry, or the x coordinate of the vertex, I would use x is equal to negative b over 2a. So we're going to go ahead and plug this in. A is equal to 3, b is equal to 3, and c is equal to negative 2. So in this case, it's going to be negative 3 over 2 times 3. The 3's can cancel out, and we'll be left with negative 1 over 2. This is going to represent two things. It's going to represent our axis of symmetry and the x coordinate of our vertex. To find the y coordinate of the vertex, you're going to take this and you're going to plug it back into the original function. So we're going to find f of negative 1/2, which is equal to 3 times negative 1/2 squared plus 3 times negative 1/2 minus 2. If we simplify all of this out, this will all work out to negative 11/4. And you guys could work this out on your calculator and double check. We can also write this as negative 2.75. So it's okay to write answers as decimal answers as long as you give me exact answers, right? So this is an exact answer. The domain, we said the domain is always going to be the same, all real numbers, the open interval from negative infinity to infinity, or the set of all x such that x is an element of the set of real numbers. What else do we need? We need the x-intercepts. To find the x-intercepts, we're going to be using the quadratic formula. Now, before I start trying to find x-intercepts, I ask myself, is it reasonable to think that there are x-intercepts? So usually what I do is I draw a quick sketch. By looking at the vertex, I can tell that the vertex is going to land in quadrant 3, and it's opening up, so I can tell for sure that there's definitely going to be 2 spots where it's going to cross the x-axis. Now, I just randomly drew that. That was a sketch. That wasn't the actual graph. That was just to let me know, are there any x-intercepts? And in this case, I know, yes, there are. So I will take the time to use the quadratic formula to find those x-intercepts. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you guys remember my little song, you guys could sing it along, right? Let's go ahead and substitute all of the values here for a, b, and c. And let's simplify this out. So if we simplify this out, this will get simplified to negative 3 plus or minus the square root of 33 over 6. And this is as simplified as we can make this. You can't simplify this any further. This represents the x coordinates of the x-intercepts. So one of these x-intercepts is going to be negative 3 minus the square root of 33 over 6, comma, and that should, I'm sorry here, that should have been a 0, 0, comma, and then the other x-intercept, -3, plus the square root of 33 over 6. So those are the two x-intercepts. All right, let me see how we can write this in. I think we all had agreed while we were, teaching class, while we were having our classes in our classroom, we had said that we all said this would be all right if we put plus or minus here. And then put this represents like our two x-intercepts, right? And it looks like it's just one x-intercept, but it's actually 2 here because I put plus or minus there in between the -3 and the radical 33. So that represents those two x-intercepts the way I wrote them down below. And the range is just going to be the half-closed interval from -11/4 to infinity. And in order to do the increasing and decreasing, we should probably draw the graph first to help us. So in order to draw the graph here, we're going to need to start labeling some points to draw this. Let's start off with the vertex. The vertex, we said we could use the -1/2 comma -11/4, or we could also write it in the form of a decimal. -0.5 comma -2.75. So let's go there and let's draw a point there. I'm going to use the calculator to just go ahead and graph this to come up with a couple other, points to come up quickly, to save me a little bit of time. So I'm going to type in the function and let's see if we can just come up with a few nice points here quickly. Oh, if you still had your stat plot on, make sure you turn off your stat plot from the last problems that we were working on from 4.2. So make sure your stat plot is turned off. Also, make sure that your zoom, that you go to number 6, Z standards for zoom standard, to get back to the standard window so that this graph comes out nicely. Just in case you haven't reset everything back to normal. All right, there's our graph. I'm going to look at the table of values to see if there's any nice values that I can use to help me sketch this graph out. And looking at this, yes, there are some nice integer values that will fit nicely on my graph so that I can quickly plot this. So I'm going to go ahead and use some of these ordered pairs that I have here, like these smaller values right here, nice integer values. I'm going to go ahead and copy this as an image, and I'm just going to go ahead and paste it on the notes. Let me just double check and make sure my vertex is correct while I'm at it right here. Let's go second, calculate. We're going to find the minimum. So minimum, it says left bound, you got to be on the left-hand side of the vertex. And then right bound, you got to be on the right-hand side of the vertex. And it says minimum is -0.5, comma, -2.75. Yes, we got it right. So we do feel pretty good about all our work that we've done so far because we got the same vertex that the graph came up with. So now that I came up with that vertex, I feel pretty good about going on here and plotting some of those other points here. Oh, let's find the zeros. Oh, so this is my x-intercept, that -1.457. I got the exact value by using the quadratic formula, but this is also another thing you could do to check your work. We can plug in what we got, -3 minus the radical 33 over 6. And if I work this out, it gives me that same decimal right here. So it's just a way for me to double check my work. Let's go ahead and check the other x coordinate. -3 plus the square root of 33 over 6. I get 0.457. Let me check on the graph and see if I end up with that same x value for that x-intercept. Let's go to 0. Left bound, I need to be on the left-hand side of this other x-intercept. Right bound, I need to be on the right-hand side. enter for guess. And yes, I get 0.457. Yes, it's the same exact value that I had from when I did the quadratic formula. Now the value that I got from my quadratic formula is an exact value, whereas this is an approximation. So we know that we always prefer to use exact values when we're given answers, unless it's specifically asking for an approximation. I'm just going to go ahead and make this a little bit smaller just to make a little bit more space here, because this is taking up a lot of space. This looks much nicer, yes. Okay, now that we have some extra space there, that looks much nicer. Let's go ahead and finish graphing this parabola. Okay, I'm going to start off with this first point here. Actually, all of these points that I'm highlighting, those 4 ordered pairs, those are the ones I'm going to use to help me graph this. Let's go here first. So it looks like I've already got 0, -2. That's the y-intercept. I already have that one plotted there. And I've already got the vertex too. And they gave me the vertex in... Oh, no, that wasn't provided in there, but let's go ahead and plot those other points. And I've got -1, -2. I've got -2, 4. And I've got 1, 4. Okay, so 5 points. That's what I like to have for a parabola. I like to have 5 points. Let's go ahead and connect those points. There you go. There's our function. I'm going to label my ordered pairs. That's 1, 4. This is -2, 4. This is 0, -2. And this is -1, -2. And then my vertex, that was -1/2, -11/4. Or you could also write that one in decimal form, right? We talked about that. The axis of symmetry goes right down the middle of this parabola. So I'm going to draw that with a dashed line. And the equation of the axis of symmetry in this case is going to be x equal to -1/2. All right, so I think we've got everything labeled out nicely. Now let's try to figure out where it's decreasing. So I can see it's going downward here from the left to the right, all the way down to the vertex, and then from to the side it's going upward. So it is going to be decreasing on the left-hand side and then increasing on the right-hand side. Remember, in order to tell whether it's increasing or decreasing, you have to read the graph from left to right. It's decreasing from the half open interval from -∞ to -1/2. It's going to be open on -∞, closed on -1/2. Increasing from a half closed interval from -1/2 to infinity, closed on -1/2, open on infinity. And this vertex here in this case represents a minimum value. So that's going to represent a local minimum. So the way we like to write this out, we like to say the minimum value is going to be basically the y value of the vertex. So I would say that this function has a local minimum of -11/4. And if I wanted to state the location, I would say at x equal to -1/2. So this is the way I would write it out. The important part here is the y value is the minimum, and sometimes you're asked to also state the location of the minimum. Not always, but sometimes. Or sometimes they might ask you to write the minimum as an ordered pair. It just depends. All right, so let's go on to the next problem. Number 4, determine the quadratic function whose graph is given. So we're going to have to figure out the equation of this quadratic function. We're given the vertex 2, 1, and we're given the y-intercept 0, 5. I'm going to write down the general form. Actually, I'm going to write down that general vertex form. But before I do that, I'm going to write down these two ordered pairs that were given to me, 0, 5, and the vertex, which was 2, 1. The 0, 5, that's going to represent a value of x and a value of y. And the vertex, I'm going to label the vertex as h, k, because remember in that vertex form, we used an h and a k to represent the vertex values. F of x is equal to a times x minus h quantity squared plus k. Now it's just a matter of substituting in. I'm going to substitute 5 for f of x because that's the y value. I'm going to substitute 0 for the x. I'm going to substitute the 2 for the h. And I'm going to substitute 1 for the k. Notice that the only value I did not substitute for was the a. That's the value I'm missing. So once I substitute everything in, I'm going to solve for a. Okay, so I'm ready to isolate the a. I'm going to subtract 1 from both sides. I have 4 is equal to 4a. I'm going to divide both sides by 4, and I will end up with a is equal to 1. Since a is equal to 1, I don't really have to write down that 1, right? Because whenever you don't write down a number, there's usually an imaginary 1 there. I'll write down the 1 for now, just so you can see it, but I'm going to erase it shortly. So I'm going to write f of x is going to be equal to 1. But the 1 we said, oh, we really don't need that because that's the a, and it's going to be in front of a set of parentheses. So it's okay if we don't write down that 1. So I'm going to go ahead and just erase it and write x minus h, but instead of h, we're putting 2, quantity squared plus 1. So this is going to be our equation for our parabola. So this is the way you would figure out the equation of a parabola if you're given the vertex and one other point. All right, let's practice finding a maximum or minimum value of a quadratic function here. 5, a projectile is fired at an inclination of 45 degrees to the horizontal with a muzzle velocity of 100 feet per second. The height h of the projectile is modeled by h of x is equal to negative 32x squared over 100 squared plus x. Because it's a negative value here, our negative a value, a is less than 0, it's a parabola that basically opens downward. When you have a parabola that opens down, then that means we basically are going to have a maximum at the very top. So when it's asking for this first question, right? Well, first of all, it says where x is the horizontal distance of the projectile from the firing point, right? We know that's what x represents. A is saying at what horizontal distance from the firing point is the height of the projectile a maximum? You're basically looking for the y value of the vertex, but we already know how to find the vertex, right? We have a formula for that. So let's go ahead and find the vertex. We're going to start off by finding the x coordinate, because that's the one we have a formula for. And then once you find the value for the x coordinate, you plug it back into the original function, and that'll give you the y coordinate that we're looking for. All right, so let's go ahead and plug in for our A and for our B. This will be -1 over 2 times A. A is that -32 over 100 squared. Now we have to just simplify this complex fraction. I'm going to multiply by the reciprocal. A negative divided by a negative is a positive, so I'm not going to write those negatives down anymore. So we're going to get 100 squared divided by 64. Now, if I were to put this into the calculator, if I wanted to see if I can get a nice decimal value for this, right, I could plug in 100 squared and then divide that by 64, and I get, just give me a second to come up with this answer. Here it is, 156.25. Now, I got a little excited here and I started doing part B here for where part A is at. But this is actually showing the step for finding the maximum height. The 156.25 actually represents the horizontal distance from the firing point. And this h of 156.25 represents the height of the projectile at that horizontal distance. So this is like the y value of the vertex. So because it says feet per second, I know it's talking about feet. So we're going to label these with the units of feet. So it's going to be 156.25 feet. And that's going to represent the horizontal distance from the firing point. Now the second part here, I told you I accidentally goofed, so why don't we just go ahead and move all of this down here to represent part B. Hope you guys aren't writing in pen. Not funny, I know, I'm sorry. Let's go ahead and write our answer nicely. This always impresses me when students do things like this on their tests. The height of the projectile is a maximum at the horizontal distance of 156.25 feet. So this looks very nice and very impressive, and it shows that you understand what you're doing. It shows that you have an understanding of what you have found. It shows that you have confidence in your work. You're always trying to do things like this to try to impress your professors. So this shows that you're willing to go like above and beyond. The maximum height of the projectile is going to be that 78.125 feet, but let's go ahead and write out a nice sentence as well for this one. The maximum height of the projectile is 78.125 feet. And then C says, at what horizontal distance from the firing point will the projectile strike the ground? When it says strike the ground, that means it's going to basically have a height of 0. Because what's the height of something when it's on the ground, right? That's what h of x represents. H of x represents the height from the ground. So what we're basically going to do is we're just going to replace our h of x with a 0, and then we're going to solve for our x. So every time I see h of x, we're just going to replace that whole thing with a 0, right? And the reason we're doing this is because we said, when it said here, strike the ground, you're talking about the ground level, and you're saying, well, what's the height at the ground level? Height has to be 0 feet from the ground. All right, so what we're doing here is we're going to factor out a negative x. And we're going to be left with a 32 over 100 squared x minus 1 inside the parentheses. I'm going to set each one of these factors equal to 0. So the first one, if I were to set that negative x equals 0, I would just get x equal to 0. But because it's saying from the firing point, then it's not really, we don't really want to include that one. We want the one after it gets fired. So if I take the second factor, set equal 0, this is going to give me the one answer that I really want. So this will give me x is equal to 100 squared over 32. And if I were to put that into my calculator and evaluate that, I would end up with 312.5. So this is the horizontal distance from the firing point when the projectile will strike the ground, 312.5 feet. All right, now we're going to graph this function, and we're going to use our graphing calculators to check and see if all of our other results that we've gotten so far up to this point, are they any good? So it's telling us here that for our window, we want to have x greater than or equal to 0 and x less than or equal to 350. So I'm going to do, for my x min, I'm going to set that equal to 0. My x max is going to be set equal to 350. And what I'm going to do, I think for my scale, I think I'm going to go up by increments of 5 so that I don't have just a bunch of, my little tick marks aren't separated by increments of 1. For my y min, I think I'm going to use, why don't we go down below, a little bit below the x-axis. How about like negative 25? I think that one would seem reasonable. So the way I'm trying to figure this out is I'm trying to say, if they told me to go up to x equal to 350, I'm trying to think in my mind, well, I should get something kind of close to like f of 3 or h of 350, right? So I'm thinking like maybe negative 25 might be good there. And then my max, I'm going to go up to 90 just because I already know what the max height's at. The max height's at 78.125. So I'm just going up above that one a little bit. And my y scale, I'm going to go up by increments of 5. So that, once again, that negative 25, I was just kind of thinking in my head, like what f of 350, or you could plug that into your calculator real fast to get an idea of if you want to get that value to match up with the 350, just in case it's important, because if that was given to us in our instructions, want to be a little bit careful, when we set up our window. All right, so I'm going to go ahead and input my function for y sub 1. It's going to be equal to whatever my h of x was. So it's that negative 32x squared over 100 squared. And then we're going to add an x to it. I'm going to change my window. So I already told you what I was going to do with my window here. We're going to have x min equal to 0, x max 350, x scale, I'm going to go up by increments of 5. My y min, we said negative 25, and then the y max, I think we did 90, and the y scale, we're going to go up by increments of 5 as well. So let's go ahead and graph that. So this is the graph that I got here. So let's double check this and see if the values that I got for my answers match up with what my graphing calculator is giving me. Let's calculate the maximum. The maximum, remember that will give us the value of our vertex value. So let's go ahead and do that. The left bound, we want to be on the left-hand side of the maximum. Here, the right-hand side, we want to make sure your y values, you're going up, up, up. And then once you start coming back down again, that means you're on the right-hand side of the vertex. And now we're going to calculate it here. It says our maximum is x equal to 156.24999. That's not an exact value. We got an exact value. There's a rounding error that's occurring here with the calculator, and we've talked about this, how the calculator is not perfect. And sometimes the calculator, has rounding errors, but that's pretty close, compared to what we got. And I believe the y value was, if you had checked the y value, it was good with our maximum value. Let's get the 0 here. Let's get this 0 that we had just gotten for that last problem we just did. I got the 0, x is equal to 312.5. And yes, that was the same exact value that we got for that last problem that we did. So yeah, it looks like we've been doing all of our work correctly, and it matches up with what the calculator is giving us. Part E. When the height of the projectile is 50 feet above the ground, how far has it traveled horizontally? I'm going to take my function, h of x is equal to negative 32 over 100 squared, x squared plus x. I'm going to take the h of x, I'm going to substitute it with 50, because they're saying 50 feet above the ground, and h of x represents the height. And then what I'm going to do is I'm going to go ahead and set this equal to 0, because it's easier to solve a quadratic when it's set equal to 0. So we're going to have 0 is equal to all of this good stuff. Now I could use the quadratic formula here to get an answer, or I could just say, instead of that 0 there, I could pretend this is a g of x, like another function, a new function. And I want to find the values when g of x is equal to 0. So what I'm basically doing is I'm looking for the x-intercepts of this new function that I created here. So what are these x-intercepts, or what are the x-coordinates of the x-intercepts? So let's go back to the y equals button, and let's type in our new function that we just came up with. We're basically looking for where is the height going to be equal to 50. And I can see by looking at this problem, there's probably going to be two values where that's going to happen. So my new function, or my modified function that I have here, is still going to be that negative 32 x squared over 100 squared and we're going to plus x and then minus 50. Let's go ahead and graph that. You know what? I'm going to change the color to this because just in case anyone is colorblind and they're having a hard time seeing this because it's red, let me go and change the color. So let me go here. I've got different colors that I can choose from. I'm trying to think of what's a good color to use here. I don't know. You know what? I think I'm just going to stick with, I'm going to just stick with black, because I think black's a good color. Everyone can see it, right? So I think there should be no problems if I stick with that color. And I'm scared if I choose another color, some people might not be able to see it. So there's the first graph in blue, and then the second graph is in black. I'm looking for the x-intercepts. To get the x-intercepts, I need to calculate the zeros. So we're going to go second, calculate. Oops, I meant second, calculate. And 0 is number 2, so we're going to press number 2, or go to number 2 and hit enter. I'm going to toggle down. I'm going to press the down button to make sure I get on the correct function graph that I want. The right bound, I got to be on the right hand side of the x-intercept. Left bound, left hand side, I got 62.5. So that would be one of my x-intercept coordinate values. So definitely want to remember that value. Don't forget it. Next 0, go back, toggle down to the other function we have here below. Left bound, got to be on the left hand side of the x-intercept. Right bound, right hand side, and the 0 is going to be 250. So 250 comma 0 is my x-intercept. And let's go ahead and remember that value so we can write it down. All right, so once again, just to remind you, we looked for what we call the zeros on the graphing calculator. And those zeros basically just gave us those x coordinates of those x-intercepts. The x-intercepts were 62.5 comma 0 was one of my x-intercepts, and the other x-intercept was 250 comma 0. Now I'm just going to write down the actual x coordinate values. So here I'm going to write down the projectile has traveled 62.5 feet and 250 feet. So in order for the height of the projectile to be 50 feet above the ground, this is how far it must have traveled horizontally. There's two values where it's going to be 50 feet above the ground. All right, and that's it for this class, or for this section. I hope you guys enjoyed these notes. All right, till next time. Bye.